1.7 is inverse functions, and it starts you off with this. I think it's kind of complicated. In a one-to-one function, each x value corresponds to only one y value, and each y value corresponds to only one x value. In algebra class, you learned about functions, and when you look at this first mapping, when 2 goes to 7 and 3 also goes to 7, that was fine. That's still a function. All right. When we had a problem was if 2 like split and went to 7 and then also to 5. We learned that that was not a function when that x number splits into two y numbers. But for one-to-one, it's kind of the reverse of that, and this is now a problem for one-to-one. You don't want two different x numbers going to a single y number for one-to-one. And so right there, this tells me that this is not one-to-one. And so that's going to be a big deal for inverses, because if it's not one-to-one, then we can't find an inverse. So what we want is each x goes to one y. This is what we want. This is both a function and one-to-one. There's one arrow between each pair of numbers, basically. Horizontal line test is a good way of determining if it's a function. A function is one-to-one if every horizontal line intersects the graph of the function at most once. So we remember the vertical line test, but now we've got the horizontal line test. Horizontal line test shows that this is one-to-one. And this one is not. And so the upshot of that is when it's not one-to-one, we can't really find an inverse. We would have to do something extra. That's way down the line. I don't really care to do that. We would have to restrict the domain and only look at part of the graph. But the short answer is horizontal line test shows me that that's not one-to-one, and that's going to mean we can't find the function. In general, a graph that is either increasing or decreasing on its entire domain must be one-to-one. All right, one-to-one. Think about that horizontal line test. If it's increasing or if it's decreasing, it's going to pass that horizontal line test. As soon as it's, as soon as it decreases and then increases, as soon as it turns like that, it's no longer going to pass that horizontal line test, and so that one's not going to be a function. So if it's all increasing or it's all decreasing, you're fine. It's one-to-one, and it's going to have an inverse. So here are some tests to determine whether a function is one-to-one, and I think this is kind of complicated, but if f of a equals f of b implies a equals b. That means we're one-to-one. And again, you're kind of going back to that mapping, the very first example. When each x goes to one y and each y comes from one x, that's kind of what we're talking about. That's going to be a one-to-one function. So yeah, that's what this says here. In a one-to-one function, every y value corresponds to no more than one x value. To show that a function is not one-to-one, find at least two x values that produce the same y value. Like we've got 1 and 2 both going to a y value. If you've got two x values that go to the same y value, that's not one-to-one. And what that shows you is basically the horizontal line test hits two different spots. 3, sketch the graph and use the horizontal line test. 4, if the function either increases or decreases on its entire domain, then it is one-to-one. A sketch is helpful here too. I like looking at the picture. I think that makes it kind of easy. So here's the definition of an inverse function, and this again is kind of difficult to understand. Let f be a one-to-one function, then g is the inverse function of f if you have this property. So remember, this symbol is a composition, and it means we plug a function into a function. So I like thinking of it as f of g of x. And what happens with an inverse, if you think about inverse operations, if I multiply by 2, then the inverse operation of that is divide by 2. If I add 7, then the inverse operation of that is minus 7. Inverse operations cancel each other out. All right, the numbers cancel out. A times 2 is canceled out by a divide by 2. That's what we're talking about with inverse functions. And so when we look at this statement, f of g of x equals x, if they're inverse functions, then all of these numbers and all of these operations will cancel each other out. And we're going to be left with just x. So that's what that's saying. Now, the trick of it is you also have to go backwards and plug f into g, and it also has to cancel out all of those operations. Whatever the numbers are have to cancel each other out if those two functions are inverses. One function cancels out the other function, inverse functions. So I think that's a little bit tricky. And that's what we're going to use for number 2 here. Use the definition of inverses to show whether f and g are inverses. So what we need to do is basically show f of g of x and g of f of x both equal x. We're looking to see that those numbers cancel each other out. We want the 2 and the 1/2, the 2 and the 1/2 are going to cancel each other out. The 5 and the -5 are going to cancel each other out if they're inverses. So let's start with f of g of x. Is a composition of functions. What I'm going to do is plug the g function into the f function. I plug the g function into the f function, so I'm plugging this in right there. The f function says 2 times something plus 5. The f function says 2 times something plus 5, but I'm going to plug in that 1/2 x minus 5. Plug one function into the other function. And let's just clean up, and hopefully all of those numbers knock each other out. So if I distribute here, 2 times 1/2 x is x. So far, so good. 2 times minus 5 is minus 10. And plus this 5. Like terms, I get x minus 5 here. All right, so I can tell right now that this is not going to work. The definition of the inverses says that I was supposed to get x. All of the numbers cancel out. I'm just left with x. That doesn't happen. So I can tell right now I don't have inverses. F and g are not inverses. F and g are not inverses. I guess in order, if I had to fix this so that they were, maybe if I made this 2.5 right here, maybe instead of 5, if that was 2.5, I'd have 2 times something plus 5, and then 1/2 x minus 2.5. When I distribute, 2 times 1/2 x is x, 2 times minus 2.5 is minus 5, plus this 5. Now those two cancel out, and I'm just left with x. Boom, that looks good. Okay. But in order to really show that they were inverses, you would also have to come back through and plug it in the other way and make sure that works. So the other way, we'd have to say, well, g is the function that says 1/2 of something minus 5. And we would plug in 2x plus 5. And so, oh wait, I changed it. I changed the g function to say 1/2 x minus 2.5. So then when I distribute here, 1/2 times 2x is x, and 1/2 times 5 is plus 2.5, and then minus the 2.5. See how that all cancels out and gives me x? If both of those equal x, then yes, they would be inverses. But as the problem was written, they are not. I know that's kind of tricky. Does anybody have any questions with that? Find the inverse, if possible. So essentially what we're going to do for an inverse is just switch x and y, and it's going to be so easy that you're going to forget about the hard part of this question. Okay, the if possible is kind of important, because sometimes it won't be possible. Sometimes we can't find an inverse. Remember from earlier, it has to be 1-to-1. It has to be 1-to-1. And so the easiest way to look at that is each x number has to go to its own y number. And each y number has to come from its own x number. If I look at it like a mapping instead of like an set of ordered pairs, it becomes clear that this one does. This one is 1-to-1. Each x goes to one y, each y comes from one x. This one's fine. There's no problems with that. All right. This one has an inverse, and so literally all I have to do for an inverse is switch x and y. So f inverse, well, let's call it f inverse, equals -8, -2, 1, -1, 8, 2. So don't forget the if possible. This second one I don't think is possible. And let's see. I mean, I guess you can look at two different places, but if I look at these 2 points right here, -2 goes to 5, and 2 also goes to 5. That's a problem. That's not 1-to-1 anymore, okay? If you look at a graph, 1, 2, 1, 2, 3, 4, 5, and -2, 5, you know, you're going to have some graph, and I don't care what the rest of it looks like. That's not going to pass the horizontal line test. That's not 1-to-1, so there's no inverse. G inverse does not exist. Okay. You might want to say because it's not 1-to-1. That's why. All right, so we look at part C, and this looks good, right? Each x goes to one y, each y comes from one x. It's all good. There is an inverse. All you have to do is to switch it. So let's call it f inverse. And let's draw this mapping. We've got 5, 6, 7, 8. 1, 2, 3, 4. 5 goes to 1. 6 goes to 3. 7 goes to 2. And 8 goes to 4. All we did was switch x and y. If it has an inverse, we're switching x and y. If it has an inverse. Now we're going to find the equation. So this is probably the hardest part, find the equation of the inverse. First, you have to check if it's 1-to-1 and if an inverse even exists. Okay, so if it exists, we're going to, if necessary, replace f of x with y. And then this is the important step. We're going to interchange x and y. That's what we do. Switch x and y. Isolate y, and then go back into your function notation. Okay. So find the inverse if possible. Again, if possible is kind of an important step because one of these functions won't have an inverse. We won't be able to do it for one of them. And the easiest way to determine if it's possible is to look at the graph, all right? We learned basic functions, and you should know the shape of some of these things. An absolute value graph looks like this. This one is a line. It's going to cross at -7 and go upwards. This one is a disco function that's shifted up 5, so it's going to look like this. Okay. The first one doesn't pass the horizontal line test, so the inverse does not exist. DNE. The inverse does not exist because it's not 1-to-1. It doesn't pass the horizontal line test. It's not 1-to-1. Doesn't exist. Okay, but there will be inverses for the other two because the other two are 1-to-1. The other two pass the horizontal line test, so there will be inverses on those. So the steps are, if you go back up, This is really step 0, I guess, if you want. The first thing, change f of x to y. All right, so this is a y. Switch x and y. So if I switch x and y, I'd have x equals 4y minus 7. Step 2, solve for y. So I'm going to isolate y, but essentially what I'm doing is I'm canceling out the operations in this problem. See this minus 7? I'm going to add 7. I've got x plus 7 equals 4y. See how that's times 4 right there? That's y times 4. I'm going to undo that by dividing by 4. And so I've got y equals x plus 7 over 4. That's basically my answer. I'm going to replace the y with my function notation. Now notice it wasn't f, it was g. So I'm going to say g inverse of x equals x plus 7 over 4. That's my inverse. Okay. So, sometimes you can just tell. Look at the original equation, had a times 4 and a minus 7, and see how my answer has a plus 7 and a divide by 4. You can see how those operations are going to cancel each other out. Now, sometimes you won't be able to see it, but this time you can. Okay. So part C is the same deal, really. We're going to look at this as y, and we're going to switch x and y. So now x equals y cubed plus 5. You're supposed to be sensitive to the operations here. I see a cubed and a plus 5. So we're going to cancel those things out. So let's subtract the 5 over x minus 5 equals y cubed. Anybody know how to undo a y cubed? Cube root, very good. We're going to cube root. We're going to cube root to undo that y cubed. So cube root, or if you want to think about it as a to the 1/3 power, either way, but we're trying to isolate y, and we've now got it. Last step, just put it in your function notation. Notice this was an h, not an f, so we'd say h inverse of x equals the cube root of x minus 5. Now, these last couple of slides, I wish I had made some better examples. So I don't like these examples. I'm going to add a little bit of stuff. I think supplementing these will help out a lot, I think. Determine whether these two functions are inverses. And you look at the graph, and if you know what you're doing, you're going to immediately be able to tell that they're not. Okay? F and G are not inverses. But right now, you've never seen one of these, and so you don't know why at this point. Okay? But remember, when we are trying to find an inverse, essentially what we're doing is we are going to interchange x and y. That's kind of the main step if we switch x and y. And so what that does is that means that any point A, B, so if you've got some point and you switch it around, that becomes, if I just switch that point, that becomes BA on the inverse, okay? So when I look at this graph, and really you can just pick like one point, all right? And I think that's enough to tell. But let's say we pick this point right here. See that point on f of x? That point has the coordinates 0, 2. That point right there has the coordinates. And I could have picked others, but that was probably the easiest one for me to see. Some of the others are like not right on tick marks, but that one's right on a tick mark. I can see that the coordinates of that point are 0, whoops, negative 2, right? 0, negative 2, yeah? So if I interchange x and y, I've got the point -2, 0. My inverse function has to go through that point. All right, all of the points a, b on f of x, you switch them around, they're going to be ba on the inverse, and that doesn't go through, okay? That's not going to work. All of the points. So here's another one. This point right here is 4, 0 on the blue line on the function. So if you switch that around, 0, 4 should be on the 0, 4 should be on the inverse function, okay? And so the result, and the reason that I can tell immediately, they've got that dotted line drawn through there. What ends up happening is like your inverse function and your function kind of like they're symmetric with respect to this. All right, this line y equals x should come right through the middle of the two lines. And if it doesn't, then they're not inverses, and you can kind of tell immediately. All right, so I didn't think that was enough. I'm going to draw another example. So let's try to draw this. Okay, I'm going to do another example here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 1, 2. Okay, so I just kind of made up some points here. I'm going to draw, let's see, the point 1, -2 is right here. And the point 5, 0, 5, 0. So it doesn't really matter what my function looks like, but let's just say I drew this. That's f. Okay, that is the point 1, -2, and the point 5, 0. So let's say that's your function. It goes through those 2 points. I don't care what else, but it goes through those 2 points. All right, so draw that in there. If I wanted to construct the picture of the inverse, then you just have to switch the x and y stuff. Okay, switch x and y. So if I switch x and y, then that first point becomes -2, 1, right there. -2, 1. And this point becomes 0, 5. And the same thing goes for any other point you want to try on that line. And the graph of this would look like something like this. That's f inverse. But what you can see is all of these points end up, and they're symmetric. They're symmetrical to this line right here. Y equals x should run right through the middle of that graph. If those two functions are truly inverses, that line's going to run right through the middle. Okay, y equals x. And this example did not do that. Important facts about inverses: if f is 1 to 1, then the inverse exists. The domain of f is the range of f inverse, and the range of f is the domain of f inverse. Okay, but if you think about it, we say domain is the x's and range is the y's. All that's saying is switch your x's and y's. That's all it's saying. I know it's complicated to read that, but that's what it's saying. You switch the x's and y's. Okay. Similarly, if the point AB lies on the graph of f, then BA lies on the graph of f inverse. That's kind of the same deal, right? You're switching the x and y's. The graphs of these two things are reflections of each other across the line y equals x. That's what we just did. Part 4, to find the equation for f inverse, replace f of x with y, interchange x and y, and solve for y. This gives the inverse. Okay, number 6. This is kind of interesting, I suppose. It says the function f of x equals 3x minus 1 was used to encode a message. This is the message. Find the inverse function and decode the message using the chart below. All right, so kind of interesting that you can do that. Find the inverse. So we want to find the inverse. Let's call this y. Let's switch x and y. Let's isolate y. So I'm going to add 1 and divide by 3. So my inverse, f inverse of x, equals x plus 1 over 3. That's the inverse. Okay. So save yourself some room somewhere. I'm going to do an extra example. Probably should have told you that already. We're going to use this to decode the message. So what we're going to do is start with this number 11. The first letter is 11, and what we would want to do is plug in 11 into that expression. 11 plus 1 over 3, that's 12 over 3, which is 4, and 4 is going to be the letter D. Okay, D. The next number is 44. 44 plugged into our inverse, plus 1 over 3, that's 45 over 3, which is 15. And 15 is the letter O. 15 is O. So notice we've got a couple of 44s. And go ahead and fill that in twice. Next, we'll do 74. 74 plus 1 over 3, that's 75 over 3, which is 25. 25 is Y. $62. Once you get on a roll, you can kind of do some of this in your head. 62 plus 1 over 3, that's 63 over 3, which is 21. 21 is the letter U. 59. 59 plus 1 over 3, that's 60 over 3 is 20. And 20 is T. So you've got T. Notice there's another T over here. 68 plus 1 over 3, that's 69 over 3, that's, what's that, 23? 23 is the letter W. 14 plus 1 over 3, 15 over 3 is 5. 5 is E. Do you tweet? I don't know. That's a weird message. That's my least favorite part about that is that message. Maybe I should come up with a more interesting message. But it's kind of interesting to me that you can use an inverse to code and decode a message. All right, questions. I've got one more example because it's on the homework, and I didn't feel like I had one. So let's just call this example 7. And yeah, I can put it right here, I suppose. Example 7. And I'm going to draw a picture here. So try to draw it as big and as neatly as you can. All right. I'm going over to 8. 1, 2, 3, 4, 5, 6, 7, 8. And I'm going up to 5. 1, 2, 3, 4, 5. All right, so I'm just going to graph some points here. I've got here. Let me erase some of this. We've got a point right here. We can label that as 0, 5. And I'm going to have a point at 2, 4. 3, 2, 5, 1, and 8, 0. So let's connect the dots. It's going to look like this. I don't need to know what the equation is. It doesn't really matter if there even is an equation. It is decreasing. It does pass the horizontal line test, so it does have an inverse. All right. And then the question is going to be confusing maybe, because they're going to say, this is F. This is F. Whatever this picture is, whatever these points are, this is F. So I want you to find F inverse of 1. Find F inverse of 1, and that's all they give you. And so I think if you look at it, you're like, well, they didn't give me enough information because they didn't give me F inverse, they just gave me F. But what's kind of the main idea, how to get from a function to its inverse? Interchange X and Y, right? Okay. So if you interchange X and Y, think of all these points. If I interchange X and Y, I'd have 5, 0, and 4, 2, and 2, 3, and 1, 5, and 0, 8. If I'm looking at the inverse, I'm looking at all those interchanged points. So you should be able to tell me what F inverse of 1 is. What's F inverse of 1? F inverse of 1 is 5. I'm switching X and Y. So that 1, instead of being an X number, it's actually like a Y number. You look at your Y number of 1, and it goes with 5. Okay? So, all right, so maybe you don't see the pattern yet, but what if I said F inverse of 2? F inverse of 2, all I have to do is look basically right here, right? From 2 to 3. You're switching your X and your Y around. Okay, you got it? If I said F inverse of 0, that's 8. Exactly. Okay, so they're going to ask you that on the homework a couple of different times, I think. And it's not a hard question, but if I didn't do that example, I didn't know if you were going to be prepared for that. So hopefully now you are prepared for that.